stand by.
So here we are in 2020, which is a great sounding year, I have to say. And so the average age of the people in this room is 17, I think. And one way to look at change, before we go forward in change, one way to understand what change can mean is to look backwards. So I thought rather than starting looking forwards, let's start by looking backwards a little bit and see what change has been. And so I thought, well, let's imagine what change has happened since I was 17. So imagine when I was 17, which you'll probably have guessed is a fairly long time ago. What's happened since that date to this date? And let's see what changes have occurred. So I know you'll be surprised, but I was 17 in 1985. That's quite a long time ago. I mean, all of you ladies would have been born in this century and this millennium. So I was born in the previous millennium, so that's quite crazy. And 1985 was a different place to the current world. We did things differently. We were all obsessed by this Rubik's Cube. We really did wear our hair like that, like patch up there in the corner. We thought it was a good thing to do. We didn't actually dress like these sort of sophisticated American ladies. Here in Britain, we dress like this because we thought it was a really good way of dressing. That is actually Sam there in the green. And we had 4 television channels only. And we'd actually just recently got 4 because we had 3 since the 70s and we had a new one come online, so we were very excited by 4 television channels. We'd heard talk, and the television shows we were watching were very different. We just got this brand new show called EastEnders, which we were very confused by, and strangely they have exactly the same plot today as they had then. Nothing's actually moved forward. It's the same people as well, arguing about the same things. Well, there you go. So that started in 1985. So in the US, they had cable TV, but we didn't have anything like that here. That would have been like a pipe dream in those days. We were stuck with our 4 channels. But I remember hearing in the playground that in the US, they had a channel that only showed music. I thought this was like the most, what is that? How can that be? Yes, it's called music television. I thought, what the hell is that? That's the most amazing thing I've ever heard. But we didn't have anything. We just had, we had 1 hour of music a week. On Thursday at 7 o'clock, Top of the Pops. That's it. That's your lot. Now go and do your homework. But we had good music, actually. Better music than you guys have. So we had U2 and we had Queen and Madonna and all sorts of stuff. And we had Live Aid. If you can think about it, Live Aid was that year. That was the big year when I was 17. But anyway, we haven't come for me to reminisce. We've come to talk about technology. So this was what technology looked like in 1985 when I was 17. So this is the Mac 1. There's the first Apple Mac. It was actually released in late 84, just 1 year ahead, but it still really wasn't in the market until 85. It wasn't actually called a Mac 1, it was just called the Mac, because they didn't know if there'd be a Mac 2. And it was from this really tiny company that no one heard of called Apple. And a couple of people leading it and a little bit of venture capital, but no one had really heard of them. And then late in 1985, in November 85, there was a new operating system released called Microsoft Windows. And again, from a tiny company called Microsoft, 8 or 9 people in Seattle in this case. No one had really heard of these people either. In fact, there's no reason why anybody would have, on the street, have known what an Apple Mac or a Microsoft Windows was. These 2 things, amongst others, were to herald a huge revolution in the way technology worked. And in fact, they are kind of a boundary point to the way things used to happen in technology, to the way things were going to happen. But there was no way that a gentleman standing on a stage in 1985 could have predicted that. It wouldn't have been obvious. These things were very niche. No one even knew what an operating system was, etc. And it was miles beyond anybody's capability to buy either an Apple Mac, which would have cost you many tens of thousands of pounds, or a machine capable of running Microsoft Windows. But I did have a computer. So this is my actual computer from 1985. It's the actual one I used. It's called a ZX Spectrum. I learnt software engineering on it. I spent far too long using it. So this was more the kind of machine that we would have in our homes in those days. But this is my last computer I bought. So that's the first one I ever bought. This is the last computer I ever bought. It's a Samsung Galaxy S9 Plus. It's about 18 months old, so it's not a particularly new model. But so that's the first computer I bought. That's the last one. I'll come on to why that's important in a moment. Now this Apple Mac, shipped with 128 kilobytes of memory, which was extraordinarily large capacity in those days. Now the irony is that this picture of an Apple Mac, this image that I put into PowerPoint, this picture is 500 kilobytes. So you would have needed 4 Apple Macs to store this picture of an Apple Mac. Just shows you how little that is. So My phone here, my last computer, has got 256 gigabytes. So is anybody going to be brave enough to tell me how many times more 256 gigabytes is from 128 kilobytes? Take a guess, anybody? 2,000? So my phone here is 2 million times more storage than an Apple Mac 1. Okay, since I was 17, I've got 2 million times the storage here, many thousands of times more the processing speed, even 32 times the screen resolution than that full-size desktop machine in my pocket here. And also, we went from, in the previous generation, we went from room-sized computers to desktop computers. I cannot tell you what a revolution the idea of having a computer on your desktop was in 1985. It's quite extraordinary. And obviously, since then, we've moved into handheld computers. Now I can slip 2,000 Apple Macs into my pocket as easy as that. And there were no mobile phones, not even smartphones. No one had even thought of those things. So computer power was one of 3 revolutions that happened. There were 2 other revolutions. Does anybody know what this thing is on the left here? Does anybody even recognize what this is? It's a compact cassette, as we used to call it, and it's for storing music in an analog format. It stores it on a tape reel, and if you want to move to the next track, you have to rewind it with a little pencil. But when I was born, all media was stored in an analog format. And when you were born, all media was stored in a digital format. So between me being 17 and you being 17, there was a complete shift. It's almost impossible for you now to interact with analog media unless you're a kind of a hobbyist and you go out to buy vinyl for a hobby. It's not normal anymore to have analog media. You don't interact with analog music, analog video, analog text, etc. But it was all analog when I was born. And the internet didn't exist in 1985. There was a precursor to the internet, which was used in universities and in the military. But there was no internet. In fact, there was a company called Cisco, which began in 1984. It was actually founded by a lady called Sandy Lerner, and it was just the start of those days. And you could connect onto a network at around 56 kilobytes a second, which is about 1,000 times slower than you connect. But there's nothing to see anyway, because there were no services to connect to. There was no Netflix, there was no Amazon, there was no Spotify, there was no Snapchat, there was no TikTok, there was nothing. And there wasn't even any music other than Radio 1, which is not good. So look, a lot has happened. So that's just actually when I was 17 to now when you're 17. And like a whole revolution has happened in the way we sort of manage things and the way we think about things. But now let's go the other way. Okay? Let's imagine that one day you're standing on a stage when you're my age, speaking to 17-year-olds, telling them about what life was like in 2020. So what year will that be when you're my age, if you can believe that as old as that, and standing on the stage speaking to 17-year-olds? Will that be the year 2055? Okay. So imagine yourself standing on a stage in 2055 speaking to 17-year-olds, talking about what's happened. So let's have a think about what's going to happen. Now we thought about what happened from 85 to 2020. Let's think about what might happen from 2020 to 2055. Because remember, the pace of change is not only moving forward, it's accelerating all the time. So it's not even the fact that we should say, okay, I now hold a device that's 2 million times more powerful than an Apple Mac 1. And in 2055, what would it mean to have a device that's 2 million times more powerful than a Samsung S9? It's actually probably even more than that, because it's accelerating. It may be 20 or 200 million times more powerful than this device here. And where we went from rooms to desktops to handhelds, these things will almost definitely disappear into the building, into our body. The form factors will change as well. So we won't even be thinking about holding. It'll be quite funny to think you held a computer in your hand. They'll be, oh, that's a funny thing. How did that happen? So what does that happen? What does that mean to us? Well, there's a paradigm shift about to happen. Actually, everything that's happened before, all those things that happened in computers and technology, in the long arc of history, when someone writes the history of mankind in the long arc, all those will simply be precursors to, honestly, to what's about to happen, because what's about to happen is very much more fundamental than what did happen. So you might think the invention of the internet and the switch from analog to digital, that switch to analog to digital, by the way, was a one-time switch. You know, humans have existed on this planet for hundreds of thousands of years. There's only one time we ever switched from analog to digital, and that was now, and then we'll be on digital forever after that. So you might think that's fundamental. But it's not as fundamental as what's about to happen with the shift. And that shift, I think, is going to be interesting because you are going to be generation 0 of that shift. So it really is up to you how you shape this thing. So let's talk about this shift and what it means and what it is. And basically, it's a shift to a term I'm sure you've all heard about, artificial intelligence. And so what is artificial intelligence? What does it mean? Why is it fundamentally different from anything we've done before? What do I mean by a paradigm shift? What kind of opportunities and what kind of dangers will it bring us all? So we'll try and cover that now, although I'll cover that very briefly. The later speakers and our colleagues and friends from UCL will cover it in a lot more depth for sure later in the day. So things are different now. I stole this slide from Zainab. Apologies for stealing. I couldn't find a better one, Zainab. So in a traditional software engineering environment, we have some inputs and we have something we want to achieve. We have an output, and then we write a piece of software, a program, to achieve those things. Okay. So let's say I have a whole bunch of inputs to do with my health. And my blood pressure and my blood sugar levels and my lifestyle choices, and we want to figure out if I'm going to get heart disease. Well, then somebody says, well, those are the inputs, that's your desired output. Let me write a program that processes those and tries to predict that outcome. And that process of writing software is what we traditionally call software engineering, and that's what most of the people in this building are involved with. And that's actually the area that not many women take part in, for lots of complicated reasons. In fact, it's almost like a 95-5 now. But that's not that important because the new paradigm is to do something completely different, okay? And the new paradigm is in an area called machine learning. Machine learning is just one part of AI, okay? So don't confuse the two. AI is a broad term, and there's other ways of doing AI than machine learning. But machine learning is by far the most dominant way of doing it because it is delivering hugely beneficial results with very little effort, I have to say. So most people talk about ML, machine learning. And in machine learning, we do something very different. We take a whole bunch of outputs, and then we take some machine, and we ask the machine to look at these outputs and to learn what's going on. And then that machine, by looking at a range of outputs, is able to do one of two things. Is able to then in the future classify things and say, well, actually, I think this belongs to this class or that belongs to that class. Or it's able to make predictions. It's able to say, okay, well, given the data I've seen, let me try and work out what I think may happen. So in my previous example, rather than just taking my lifestyle choices, let's say we took the lifestyle choices of a huge cohort of people and we gave it all to the computer, and the computer looked over it and learnt about it and formed a model, and we'll talk about how you form a model. These seem like abstract terms, but our colleagues will show you how this is a very mathematical process. Then the machine is able to make classifications. It's able to say, well, actually, people who smoke are more likely to get it. People who are in this weight range are likely to get it. People of this ethnicity are likely to get heart disease. And it can make predictions. It can say, okay, well, based upon the model, and based upon you, I think you're in this part, you're this probabilistically likely to get it. So it's a very fundamentally different way of doing things. And the important point for you is it doesn't really involve any software engineering, I'm afraid. It's bad for me, because I spent my whole career writing programs. It involves maths. It involves exactly the maths that you are familiar with. It involves matrices. It involves calculus, algebra, geometry, probability, topologies, all these things you'll be learning now, and you'll be hopefully learning at university and other things. It's a pure mathematical process, and hence it's a lot easier, I think, for people of your skills to deal with. And it's literally 1,000,000 times easier to take a mathematician and to train them to do the little bit of software engineering they might need to do than it'll ever be to take a software engineer and train them in the maths that they need to learn. So, companies like Cisco are very, very keen now that people start progressing their mathematical skills because that's the skills cliff we're heading for. But what does this mean in practice? You might say, Peter, I still don't get it. Let me look at another practical example, handwriting recognition. Okay, so here's a piece of handwriting, and here's the equivalent digital text which a computer has worked out. So how do we do this? So imagine the complexity of writing a computer program to process handwriting. We tried actually to do that for decades. It's really hard and it never really worked. But now we don't use a writing computer program, we use machine learning. We give the computer thousands and thousands and thousands of examples of handwriting. And we let the computer form a model of what that handwriting is. And we let the computer come to its own understanding of what that handwriting is and how it needs to relate that. But you have to give a lot of source data to the computer for it to build a model to do that. Now, you might say, well, how does that happen, Pete? How can a computer actually understand this text? Like, are we talking about some kind of scary AI that we see on films where computers are kind of like telling us what to do? It's really important you understand that we're not talking about general intelligence. We have general intelligence, okay? And in fact, you can't separate your general intelligence from narrow intelligence, but a computer only has narrow goals. So the handwriting program has a narrow goal of translating these things, which it only sees as images and vectors and pixels, into some digital format. It doesn't really understand. So when I show you this picture, you intrinsically, because you're humans, subjects of millions of years of evolution, you can't separate a real-world understanding from the problem. You look at it, you make subjective judgments about the quality of this person's handwriting, you recognize that it's written in a thick black marker, you know it's written on a paper substitute, you can see it says week 50, so you think, oh, this is probably one of many he wrote. You know, you'll scan over it and see it contains the word Disney, and that will suddenly fire off a whole bunch of neurons in your brain about what Disney means. You can't look at this without general intelligence. But a computer doesn't see any of that. It simply sees vectors, images, and processes it that way. And you can try this at home yourself. So there's a thing called Google TensorFlow, which is free. You can download it on your computer, and it takes you step by step through how you make models. And there's a specific one about handwriting recognition of digits. It gives you hundreds or thousands of examples of handwritten digits, and you can interactively create a model that understands those digits and then can translate them. And then you can just go ahead and write digits and see the computer tell you what you're doing. So the fact that you can do this interactively now, building a model, just shows you how far we are from software engineering days. But it still might not make some sense. So we're going to try it. We're going to try and do some interactive machine learning right here, just to sort of make the point about how the process works. Okay? So bear with me now. So here's an image that makes no sense at all. Okay? It means nothing because I'm trying to subtract your general intelligence and narrow you down. It's just an image of some things. And each one of these things, each one of these 8 things is a foo. Okay? So look at this. It doesn't mean anything. You're looking. I'm glad you're looking quizzically because that's the way the computer behaves. Just look at these images and just train your mind to think, okay, these are all foos. Okay? And these 8 images are all bars. That label means nothing as well. Okay? So these are foos, and these are bars. Okay? Foo, bar. Okay. So is this a foo or a bar? So this is a bar, very obviously. It's a very simple example of a bar. And this is a foo. This is so much a foo you wouldn't believe. This is more a foo than the example foo. It's like classic fooness. What is this one? This is a foo on balance, yeah? I agree. This is a bar. And now a hard one. It's hard. This one's quite difficult, actually, to classify. You don't know which one it is. And this one's even harder, actually. Yeah, so it's a bit harder to classify. So what's happened there? So what's happened was you took images you had no understanding of, no real understanding of what they were. You didn't know what the labels meant. But nevertheless, you made a structure in your mind which is a classifier of those images. So in your mind now, there is a physical structure, which we just built together, to classify foos and bars. And all our understanding of neurology means that structure in your mind now will be with you forever, till the day you die. There'll always be something in your mind to classify foos and bars. Whether you think it's relevant and surface it is another matter. But we've just made a physical structure in your mind, constructing of neurons and the synapses for classifying foos and bars. But you have no idea what foos and bars are. But yet you can become quite adept after a while at classifying foos and bars. You can become the world's expert at foo bar classification. And this is the world as the computer sees it. It has no real world understanding of what it's doing. It's doing a narrow classification problem and simply looking at the world like that. You actually can't do that. Even on this image, because you're human, you can't do that. Here, even when you look at this image, you have a natural bias for reds over greens. You have a natural bias for squares over circles. It's almost impossible for humans to look at things in pure abstract terms, but computers do look at things in completely abstract terms. Now, this is 2 images, 2 colors on a 2-dimensional plane. What if we played the game with 3 images and 3 colors in a 3-dimensional space? And I said, look at that. And you think, oh, okay, that's going to be a bit difficult. In fact, it's going to take me a while to even classify it, because I have to so it's going to maybe 10 times harder for you to do that than it was to do a 2D. What if it was 100 images and 100 colors in 100 dimensions? At which point you're saying, now you're just being stupid. You can't even imagine more than 3 dimensions. We don't have a brain structure that can imagine 4 or 5 dimensions. But guess what? The computer doesn't care. The computer doesn't care because maths doesn't care. Our world is 3-dimensional, but our maths isn't. If you want to have a 4th dimension, fine, just have another parameter on there. It still works. You can still do your Euclidean geometry in 10 dimensions. It doesn't actually affect the mathematics at all. If you want to run time backwards, it's fine. Just give time a negative value and you can run it backwards, but you can't run time backwards in. So this is where we reach the limits of what we call human cognition. Humans are bound up in our biological bodies, and we can only think about things in human terms. And we get bound in by human cognition barriers. But maths is not subject to that barrier, and hence computers are not subject to that barrier. So if you want to imagine, if you want to build a model that examines 100 different things in 100 dimensions with 100 axes, fine, knock yourself out. The computer won't care. It just takes longer for it to run it over it. And this is an illustration of that. Can anybody guess what links these 8 people? Anybody? Somebody take a guess. Sorry? Brown hair? Oh, they have all got brown hair. You're right, actually. They've got dark hair. No, but that's not the link. The link is that none of these people exist. They're not people. Not only do they not exist today, they never existed. These people never existed because they're not photographs. They're drawings. They're drawings done by a computer. They're drawings done by a computer which analysed so many millions of faces and built such a complicated model over faces. It said, guess what, guys? I got this. I know what a face is. And we said, if you know what a face is, draw one. It's all right, a random one. Yeah, well, here you go. Here's a random face. And these are just random faces drawn by a computer. These people never existed, I'm afraid. So be careful about the pictures you look at online. These people never existed because this is simply a drawing by a computer. Now, if I showed you, if we went to the V&A and we went around and we looked at pictures on the wall from our history of artists, and I said to you, well, these people in this picture never existed, then you wouldn't be surprised. You wouldn't be looking at me surprised. You, well, what's fine? I'm sure that Turner just invented this man on a hay cart. What's the big deal, Pete? And the difference is to do with fidelity and complexity and scale. Because the computer is doing nothing different to what Turner did when he drew random people. It's just doing it on a phenomenally high fidelity, micro scale with hugely complex models. And so that's challenging, and that creates its challenges for us. And we can look at complexity. Okay, I'm not sure why 2 came up. We can look at complexity here. This is another example of complexity. So the first game here, it's only supposed to show 1 game. I'm not sure why chess has come up. The first game here is noughts and crosses, which our American colleagues call tic-tac-toe. Okay, very simple game. Nobody plays it anymore. You probably played it when you're younger because it's always a draw, because it's so simple. But in terms of complexity, there's only 255,168 combinations. That's the total number of grid combinations, which is a very small number in computer science. So the best way to solve it in a computer is simply to have a list of all possible games. Just have a big table of all the possible games and the best next move, and then you just run that. And it's not even a program. It's not really an algorithm. It's just a lookup table. You can say, look it up, do that move, look it up, do that move. Okay, and then the game will always end in a draw unless the other player is really poor. Okay, so no complexity at all. But chess is on a different level, because in chess, the number of combinations is now immense. It's billions of combinations. You couldn't possibly list them out on the table anymore, so you can't use that strategy anymore. But nevertheless, from any given position, there's only a certain number of valid moves you can make. Okay, so from this position, maybe there's only 12 valid moves. And given you make any one of those 12 valid moves, maybe there's only another 12 valid moves. So chess can be solved in what we call a tree. You can say, well, okay, you can make 12 valid moves, and from those 12 you can make this 12, from this 12 you can make this 12. So you can make a tree of possible moves, and then the depth of that tree is how many moves ahead you're thinking. And that's exactly how computers traditionally solve chess problems. You can do it. It's very standard computer science. You don't need machine learning. And Deep Blue, a program from IBM in 1997, beat Garry Kasparov, the then reigning chess champion. And so 1997 is when we lost chess to machines. And it did it through an exhaustive tree search. It was simply thinking 100 moves ahead. And Kasparov, clever as he is, was probably thinking like 8 or 10 moves ahead. And he's probably the most able to do that. But then we get to this game called Go. So Go is a game that's played in Korea, China, and Japan. And here the number of combinations, even on a tree basis, is impossible. Even the tree would explode. It's impossible. You would need more than the current age of the universe to process Go using the Deep Blue algorithm. It just is not possible. So this is where we switch to a different paradigm. So this is where we use machine learning. So Go was thought to be impenetrable for a long time, but we use machine learning. There's a company called DeepMind just down the road from us now, often called Google DeepMind, but it's not a Google, it's a bona fide British company. They trained a model to play Go. It trained it by playing itself over and over again and making a mess of it, and eventually it got better and better and better at it. And in 2016, AlphaGo beat the reigning human champion at Go. So Go is now gone. But there's a fundamental switch between chess and Go. It's a switch between traditional software engineering and machine learning. There's no way you can solve Go using traditional engineering. You have to use machine learning. There's no other way it can be done. But then we come on to this game, poker. Now, poker is a very different game because it involves irrational gameplay. It involves lying, and it involves conceit, and it involves hiding some information. Okay? So you have some information which the other players don't have. You can bluff. You can pretend you have more than you have, etc. So it's more of a human game. And so you might imagine that at least these non-deterministic games can stay within our realm. Okay? We might have ceded control of chess and Go, these deterministic games, to machines, but poker is ours. Not so. Last year, for the first time, machine learning algorithms were beating professional poker players, not amateur players online, professional poker players, by examining their play, even examining subtle elements about how long they were taking to make betting decisions. Right now, people are working on very sophisticated face recognition, which will watch you while you're playing. You know, the idea of poker face. So a poker face, which you might have heard, means you don't give anything away. So you look at your cards, and you look up, and you don't give away from your face that you've got two aces or two twos. So machines are now watching faces, and then they'll only get better and better at that, looking at tiny micro gestures in the face to see if people are lying. So poker's gone as well, I'm afraid. So AI. So that's what we're talking about, eh? And there's huge advantages in having AI. There's advantages in medicines. We'll all be healthier. Our drugs will be more effective. We'll be better at predicting what's going on. In Japan now, we saw a great example of something called CareBots, tiny little robots dressed up as teddy bears, which children play with and talk to. But these teddy bears are actually nurses which are continuously monitoring their health, their anxiety levels, and their heat and their vital signs. We'll see changes in social care. We saw some great suicide prevention AI, which can examine people's online posts and try and predict if they're in a bad place. We saw a really great AI that watches people on train station platforms and predicts whether they're about to commit suicide there because they have very formulaic behavior. Transportation, autonomous vehicles, conservation. We're involved in a huge project to protect rhinos from poaching using AI and ML. Honestly, endless advantages. But dangers too. So let me tell you about some of the dangers. Some very significant dangers as well if we don't do it properly. And the dangers are that we end up having winners and losers in AI. And that we end up taking our own human frailties and baking them into a computer and scaling them up by 1 million times. Or we end up taking the natural societal imbalances and reflecting them back onto ourselves. So here are a few examples. So somebody made a camera, and they thought it would be great if the camera told you if the person you were taking a camera on was blinking, because then you know, okay, that's not a great shot, I need to take another one. So the camera says, is somebody blinking? Well, guess what? Half the world's population has a different eye structure to people who made the camera algorithm. So this Chinese, I think, lady is always shown as blinking by the camera. Okay, so this is not good. The people who constructed this model didn't really think it through. They didn't source enough training material, we would say. Here's one about who's likely to default on a loan, okay, by ethnicity. Well, it turns out defaulting on a loan is actually related to ethnicity, but it's only related to ethnicity because it's related to poverty. And the structural reasons why some ethnic groups find themselves in poverty. Okay, so maybe we deal with that. But if we just let the computer deal with it on its own basis, it will simply magnify that by rejecting those people. And so you'll take something that was a human problem and it will just make it 1,000 times worse. It'll just bake it in, so it becomes an invariant now. And that's because we have what we call an open world assumption. We always assume there's some other knowledge from the demand narrow thing we're looking at. Like I might say, oh, these people are known. You say, but Pete, it's more complicated than that. There's other facts. But the computer has a closed world assumption. It can only see what it sees. Okay, so it's going to make very, very clumsy decisions. In the US, they actually tried to use machine learning to do something called recidivism. Recidivism is predicting whether somebody should be let out of prison, whether they're likely to reoffend. And the algorithm was racist. There's no, I can't dress it up any other way. It just genuinely predicted that black people were more likely to reoffend than white people in a consistent fashion. Nobody did it inadvertently. It was just a funny factor of the way the training material was put together. But that's what it said. Black people were consistently more likely, it said, to reoffend than white people. But the data didn't show that when you examined the outcomes. Okay, but it's an important point here is that we are also frail. These decisions are currently made by humans, and that's not to say humans are making any better decisions than people. I mean, I personally think the guy there looks pretty ropey. I don't think I want to, be on a tune, but that's just a human frailty. There's no reason he might be the best person in the world. I don't know. So we are also subject to these frailties. Amazon thought it was a great idea to use an MN algorithm to sift all the CVs that were coming in and just surface the ones that were worth interviewing. And it turned out it was rejecting most of the women who were saying, yeah, these people don't look good to me. And so it was a sexist algorithm. And again, it didn't mean to do that, it's just the way it worked out. In fact, the gender wasn't even on the CV, but it indirectly worked out the gender by looking at the subjects they were studying, their interests and things like that. And it said, okay, well, we don't want these candidates, we do want these ones. So it was kind of going for a so these are kind of examples of the dangers that can occur. And these dangers are quite real, actually, and they're happening all the time right now, even though we're in early days. And the important thing is that if we're going to have computers sitting in judgment of us, if they're going to be sitting in the judge's chair or if they're going to be sitting across the interview table from us, we want to have confidence that they're making those decisions in a reasonable way. And there are many ways to do that mathematically, but the most effective way of doing that is to make sure a diverse set of people built the model in the first place. Okay? If all the models that govern all our future are built by men, then you're going to end up in a very brutal world, I think. You need a diverse set of people from a diverse set of backgrounds thinking widely about the world in order to build this technology in its most effective way. Okay? And that's why it's very important that women take part in this technology in an equal way, not in a token way, in an equal way. So we know that we're building much more inclusive models for these kind of things. I mean, we talked a little about 1985. Trust me, if we had baked in the attitudes of 1985 and we were stuck with them forever, it would not be a great place. I was there in 1985. It was pretty brutal at times, I have to say. So anyway, change is coming. It's a really great time to be your age, I have to say. It's a really great opportunity. Absolutely, hopefully you've seen that people of your skills have all to play for, and absolutely, hopefully you've seen that why people of your gender need to be taking part in these technologies. And hopefully we'll build on that, you'll see a lot more of that in the coming speeches. But last slide, let me just reflect on ladies in technology. So does anybody know any of these people? Can anybody name one person?
I think the bottom left is
Hedy Lamar, you're right. It is Hedy or Hedy Lamar, I'm not sure how you say it, it's Hedy Lamar. And do you know why she's on the slide?
something to do with like the internet or the Wi-Fi.
Yeah, that's a pretty good one. Ada Lovelace, yes. And do you know why she's on the slide? She did right. So let's just have a look at it. So this is Ada Lovelace, who was a peer of Charles Babbage. She wasn't his junior or his secretary, as people say. She was a mathematician, and she wrote the very first computer algorithm. Not only did she write the first computer algorithm, she was the first person to work out that you could encapsulate problems algorithmically. Okay. Nobody had quite thought about it in those terms before, so that's a great person to know. The person immediately to the left of her is Grace Hopper. Grace Hopper was a Rear Admiral in the US Navy, and she was also a mathematician, and she was a pioneer of computer technology, and she was one of the people behind the UNIVAC 1, which was one of the first giant industrial computers that were used by the American military. And she wasn't just a bit part player, she actually led the UNIVAC program for some time. The person on the left of her is Melba Roy. Melba Roy is a mathematician. She wrote all the mathematics that governs the way satellites circle the Earth. She was one of the first people to do it. Her maths is still the maths we use today. She worked for NASA in those days. The lady below here in the corner is Hedy Lamar. Hedy Lamar is a very famous actress from the 1940s. If you haven't seen any of the films, you probably haven't missed anything. They weren't great. But she was also a mathematician, and she patented the technology which now underlies Wi-Fi. So whenever you're using your phone, you should raise a cheer to Hedy Lamarr. The lady immediately to the left of her is Katherine Johnson, that's right. So Katherine Johnson was a mathematician. She worked at NASA. She worked out orbital trajectories. She did the trajectory for the John Glenn, which is the first US flight, or first manned flight? First US flight, I think, in space. And you'll have seen her if you've watched a film called Hidden Figures. She was a great person there. And then the other lady here is Katherine Johnson. Katherine Johnson also worked at NASA. She was one of the teams. She was also a mathematician. She was one of the teams who wrote the software which piloted the first Apollo space programs. And the thing she's standing next to there is actually a pile of printouts for the software control system of the Apollo system. So she was part of the team that wrote that. So hopefully what you've noticed here is they're all mathematicians. And in fact, ladies took a reasonable part in technology whilst it was maths. It was something about the shift to computation and algorithmic approaches which somehow excluded them. But that, anyway, is changing. I think we're coming back to it being a maths problem. So that's it. So that's all I have to say today. Hopefully it was all sort of a good introduction to the day and makes a little bit more sense about what we're trying to do and what we're trying to achieve. I'm not sure if I overran or anything.